the mechanics of expansion, sign convention, and minors. Welcome back, everyone. In our previous lesson, we explored the fundamental idea that a 3x3 determinant isn't just a single block of numbers, but can actually be broken down, or expanded, into a sum of much smaller 2x2 determinants. Now, while the concept sounds straightforward, simply breaking them down isn't enough to get the right answer. To do this accurately and avoid errors, we must follow a specific mathematical protocol, essentially, a set of rules that ensures our expansion is mathematically sound. Today, we are going to master the two primary components of this protocol. First, understanding what we call the minor, and second, mastering the sign convention to ensure every positive and negative sign is in its proper place. Understanding the minor of an element. Now that we know a 3x3 determinant can be broken down into smaller parts, we need to look at the first essential step. Before we can actually calculate the determinant, we have to learn how to isolate a specific element within the matrix. This brings us to a key concept called the minor. Think of a minor as the determinant of the smaller matrix that remains after you delete a specific row and a specific column from your original matrix. To make this clear, let's look at the step-by-step process using a general example. Suppose we have a 3x3 matrix, which we'll call matrix A. This matrix is composed of elements arranged in 3 rows and 3 columns. In the first row, we have a sub 1-1, a sub 1-2, and a sub 1-3. In the second row, we have a sub 2-1, a sub 2-2, and a sub 2-3. And finally, in the third row, we have a sub 3-1, a sub 3-2, and a sub 3-3. In the next slide, I will show you exactly how to perform the deletion process on this matrix to extract that minor. Finding the minor of an element. Now that we have our $3 times $3 matrix A in front of us from the previous slide, let's walk through the actual mechanics of how to find a minor. Let's focus on the element a sub 1-1, which is the element located in the very first row and the first column. First, you need to identify the element. Simply locate a sub 1-1 on your matrix. Next, we perform the deletion step. Mentally, or even physically with a pencil, cross out the entire first row. Once that is done, go ahead and cross out the entire first column as well. Finally, look at what is left behind. The remaining 2x2 grid of numbers that hasn't been crossed out forms our new, smaller determinant. This is what we call the minor, and we denote it as m sub 1-1. In the next slide, we will see exactly what that looks like visually. Example of a minor. Now, let's put that theory into practice with a concrete visual. If we look back at the element $11, which is our top left element, and apply the deletion process we just discussed, we can see exactly what remains. By crossing out the first row and the first column, we are left with a smaller 2x2 matrix. We call this remaining piece the minor of $11, and we denote it as M11. As you can see on the screen, M11 consists of the elements $822, $823, $832, and $833 arranged in their original relative positions. This little 2x2 determinant is the foundation we'll use for the rest of our expansion. In the next slide, we'll move from this abstract notation to a real-world numerical example. The sign convention, the cofactor rule. Now that we understand how to isolate an element and find its corresponding minor, we need to address a crucial step that often trips students up. In determinant expansion, we do not simply multiply the element by its minor. If we only did that, our final answer would likely be incorrect. We must also apply a sign, either positive or negative, based specifically on the position of the element within the matrix. This rule is governed by a specific mathematical formula. The sign factor equals -1 raised to the power of I plus j, where I represents the row index and j represents the column index. In the next slide, we will break this formula down to see exactly how it works in practice. Breaking down the sign factor. Now let's break down that sign factor formula so you know exactly how to use it. First, we need to identify our variables. The letter I represents the row index, which is just a fancy way of saying which row the number is sitting in. The letter J represents the column index, or which column the number is in. To find your sign, you simply add the row number and the column number together. If the sum of I plus j results in an even number, then the sign factor becomes positive, because -1 raised to an even power equals +1. However, if the sum of I plus j results in an odd number, the sign factor becomes negative, because -1 raised to an odd power equals -1. Don't worry, though, as we will see in the next slide, there is a much quicker way to visualize this without doing the addition every single time. The checkerboard pattern. Now I know what you might be thinking. Calculating -1 to the power of I plus j for every single element sounds like a lot of extra work. And you're right, it can be quite tedious during an exam. So, here is a much more efficient shortcut. Instead of performing that calculation every single time, you can simply memorize a fixed sign pattern for a 3x3 matrix. It looks exactly like a checkerboard. If you look at the pattern on the screen, you'll see it alternates. The top left corner starts with a plus, then moves to a minus, and then back to a plus. The second row starts with a minus, goes to a plus, and ends with a minus. Finally, the third row follows the same pattern as the first, plus, minus, plus. By keeping this checkerboard pattern in mind, you can instantly identify whether you need to apply a negative sign to your element's minor, which will make the expansion process we are about to see in the next slide much smoother and faster. The complete expansion process. To expand a determinant along a specific row, let's use the first row as our standard example. We essentially perform a 3-part multiplication for each element in that row. We take the element itself, multiply it by its corresponding sign factor we just discussed, and then multiply that by its minor. If we look at the general formula for the determinant of matrix A, expanding along the first row, it looks like this. The determinant of A equals a sub 1 1 times the minor of a sub 1 1, minus a sub 1 2 times the minor of a sub 1 2, plus a sub 1 3 times the minor of a sub 1 3. Now that we have mastered how to find an individual minor and how to determine the correct sign using that checkerboard pattern, let's bring everything together into the complete expansion process. Notice how the signs alternate between plus and minus, just like our checkerboard pattern predicted. In the next few slides, we are going to walk through a concrete numerical example to see this formula in action, step by step. Detailed example of expansion. Now that we have mastered the theory behind minors and the sign convention, let's put everything we've learned into practice. On this slide, we have a concrete problem to solve. We are going to calculate the determinant of matrix A looking at our 3x3 matrix. We have the first row consisting of 2, -3, and 1. The second row contains 4, 0, and 5. And the final row is composed of -1, 2, and 3. We will be expanding this determinant along the first row, using the step-by-step process of finding the minors and applying the checkerboard sign pattern that we just discussed. Let's move on to the next slide to break this down element by element. Step 1. Process the first element A11 equals 2. Now that we have our matrix and we know the theory behind expansion, let's jump into step 1 of our actual calculation, where we process the very first element, which is a 1, 1, or the element in the first row and first column. This element is the number 2. First, we need to determine our sign factor using the rule we discussed earlier. Since this element is in row 1 and column 1, we add those indices together to get 1 plus 1, which is 2. Because 2 is an even number, our sign factor, 1 minus 1 to the power of 2, simply becomes +1. Next, let's find the minor, which we call M11. To do this, we follow the procedure from our previous slides. We mentally cross out the entire first row and the entire first column. Once those are gone, we are left with a small 2x2 matrix consisting of the numbers 0, 5 in the top row and 2, 3 in the bottom row. Finally, let's put it all together for the calculation. We take our sign factor of +1, multiply it by our element, which is 2, and then multiply that by the determinant of our remaining 2 by 2 matrix. To solve that small determinant, we multiply 0 by 3 and then subtract the product of 5 and 2. This gives us 0 minus 10, which is negative 10. When we multiply our initial 2 by negative 10, we get a result of negative 20 for this first part of our expansion. Keep this number in mind, because in the next step, we will repeat this exact same process for the second element. Step 2. Process the second element, 812, equals minus 3. First, let's determine the sign for this position. Since this element is located in row 1 and column 2, we add those indices together to get 3. Because 3 is an odd number, our sign factor, calculated as negative 1 raised to the power of 3, results in a negative 1. Next, we need to find the minor, which we call M12. Just like we did in the previous step, we mentally cross out the entire first row and the entire second column. This leaves us with a smaller 2 by 2 matrix consisting of the numbers 4, 5, negative 1, and 3. Finally, let's perform the calculation. We take our sign factor of negative 1 and multiply it by our element, negative 3, which, as I mentioned earlier, will cancel out to become positive 3. Then, we calculate the determinant of that remaining 2 by 2 matrix by multiplying 4 by 3 and subtracting the product of 5 and negative 1. This gives us 12 minus negative 5, which simplifies to 12 plus 5, or 17. Multiplying our positive 3 by 17, we arrive at a result of 51 for this part of the expansion. Keep this number in mind, as we will need to add it to our previous result in the next step. Now that we have successfully processed the first element, let's move on to step 2, where we handle the second element of our first row, which is negative 3. Step 3. Process the third element, A13 equals 1. First, let's determine the sign for this position. Since this element is in row 1 and column 3, we add those indices together to get 4. Because 4 is an even number, our sign factor, 1 plus 3, becomes positive 1. Next, we need to find the minor, which we call M sub 13. To do this, we follow the same rule we used in the previous steps. We mentally cross out the entire first row and the entire third column. Looking at what remains of our original matrix, we are left with a 2 by 2 determinant consisting of the numbers 4, 0 in the top row and negative 1, 2 in the bottom row. Finally, let's perform the calculation. We multiply our sign factor, which is positive 1, by our element, which is 1, and then multiply that by the result of our 2 by 2 determinant. Inside the brackets, we multiply 4 by 2 to get 8, and then subtract the product of 0 and negative 1, which is 0. This leaves us with 8. So the total contribution from this third element is simply 8. Now, let's move on to the final step of our expansion, which is processing the third element in our first row, element a sub 13, which is just the number 1. Now that we have all three parts calculated, let's move to the next slide to sum them all up and find our final determinant. Step 4. Sum the results. Now that we have calculated the individual components for each of our three elements, we reach the final step. To find the determinant of matrix A, we simply sum the results we obtained from our previous steps. We take our first result, negative 20, add our second result, 51, and finally add our third result, 8. When we combine these, we get a final value of 39. So, the determinant of matrix A equals 39. This completes our expansion process, but before we finish, let's take a moment to review some common pitfalls to ensure you don't lose marks on these calculations in the future. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the theory, it is very easy to make small computational errors that can lead to the wrong final answer. Let's look at 3 specific mistakes to watch out for. First, the most frequent error I see is ignoring the sign factor. It is very easy to get caught up in the numbers and forget to apply that alternating sign we discussed with the checkerboard pattern. Specifically, students often forget to change the sign for elements like a 1-2, a 2-1, a 2-3, or a 3-2. To prevent this, I highly recommend you physically refer back to that checkerboard pattern on your paper every single time you move to a new element. Second, be extremely careful with double negatives. This is a classic trap. As we saw in our detailed example with the element A12, which was -3, the sign factor for that position was also negative. When you multiply a negative sign factor by a negative element, they cancel each other out to become positive. Always remember that -3 multiplied by -1 equals +3. If you don't track those signs carefully, your entire sum will be incorrect. Finally, watch out for incorrect minor selection. When you are calculating the minor for a specific element, you must be disciplined. You must delete the exact row and the exact column of the element you are currently processing. For instance, if you are working on the element A21, you must mentally cross out the second row and the first column. If you accidentally use the row or column from a previous step, your minor will be wrong and the rest of your calculation will collapse. Keep these 3 points in mind, and you will find much more success with matrix expansion. Key takeaways. First, let's revisit the concept of the minor, which we denote as M sub ij. Remember, the minor is simply the determinant of that smaller submatrix you get after you've removed the ith row and the jth column from your original matrix. It's that leftover 2x2 grid we practiced finding. Next, don't forget the sign factor. As we saw with the checkerboard pattern, the sign is determined by the formula. -1 raised to the power of I plus j. This is what creates that alternating plus and minus pattern across the matrix, and it is crucial for getting the correct final value. Now, let's look at the overall expansion logic. To find the total determinant, you are essentially calculating the sum of the products of 3 things: the sign factor, the specific element you are working with, and its corresponding minor. If you follow this pattern for every element in your chosen row or column, you will arrive at the correct answer. Finally, a very important point regarding consistency. While we chose to expand along the first row for our detailed example, remember that the process remains exactly the same regardless of which row or which column you choose to expand along. The result will be the same, as long as you are meticulous with your signs and minors. All right, we have reached the end of this lesson, so let's take a moment to recap the essential points we've covered today to ensure everything is clear. I hope this summary helps solidify these mechanics in your mind. Keep practicing, and you'll master this in no time.